So in this section, we're going to look at multi-stage models, and multi-stage models are where we start to put to use the things that we've learned so far over our previous lectures. And to do this, we're really just going to look at an example. So assume that there are two events. We have an event A that there's an airplane flying above, and there's a certain probability associated with that. We'll come back to that piece, but event A is that there is an airplane flying above us right now. We also have an event B that is something registering on a radar. So let's say we have a radar in front of us. We're trying to determine whether or not something, an airplane or a duck, registers on our radar. Now, to help this make a little bit more sense, let's build out a model. And the easiest model for this is going to be a tree diagram, as we just kind of look at the multiple stages or the multiple layers of this model. The first thing we'll look at is the probability of an airplane flying above. And so we have two different branches off of this model. The first being the probability of A here, the probability that there is an airplane flying above. And we'll arbitrarily assign that to 5%, 0.05 probability. And then on the opposite branch, we have the probability that there is not an airplane flying above. Now, by normalization, saying that the probabilities here have to sum to 1, we know that that has to be 95%, or 1 minus 5%. Now, after we've determined if there is or is not an airplane flying above, we can move into the second stage of our model. And in the second stage of our model, we're going to look at the probability of something actually registering on our radar. First, it's important to note that this node right here is really just A. And likewise, this node is A complement, because those events have already occurred by the time we reach that node. So we can say that the probability of traversing this branch is really the probability of, say, B, given that A has already occurred, because we've already made it to this node. So the probability of something registering on a radar in this case, given that we've already determined there's an airplane flying above, well, let's say that's 99%. And then the probability, again, has to sum to 1 here. The probability of nothing registering on a radar, given that there is an airplane, we'll say is 1%, or 0.01 probability. Now, on the other end, again, this is A complement. There is no airplane flying above us right now. We have the same type of situation. We need to look at the probability that something registers on a radar, given that there is no airplane flying above, and we'll call that a 10% probability. And then the probability that nothing registers on the radar and that there is nothing flying above us right now. And we'll give that a 90% probability. And again, these are both conditioned because we've already made it to this node. So if we wanted to assign some names to these, we can really also say that all of these are intersections. And this is what we've seen before, that if we make it to this leaf, that we have the probability of A intersected with B, the probability that both A and B occur. And if we make it to this leaf, that's the probability that there is an airplane flying above, but that nothing registers on a radar. We could call that a miss, right? Something didn't get found. Now, the next one down here, this is the probability that something registered on the radar, but there wasn't anything. This we could call a false alert or false alarm. And then this last one down here is the probability that there's no airplane and we don't register anything. So this is normal operation. Now, there's some terms that we can use for each of these states, and we would call these the true positive, false negative, false positive, and true negative states, respectively, where we can look and say that if there is something there and we see it, well, it's correctly identifying the state, and the state is positive. In this next case down here, we can say that it's incorrectly identified the state as negative. In the next case, we can say that it's incorrectly identified the state as positive. And then in this case, it's correctly identified the state as negative. And so these are terms, I wouldn't necessarily worry too much about getting familiar with them, but they are terms that you'll see as you progress further into probabilistic systems and really just engineering systems in general when you're trying to do detection. So based off of this information, let's try and find the probability of A intersected with B. Well, if we go back to our basic counting rule, we would say that we're going to take the probability that A occurred multiplied by the probability of B conditioned on A. But there's a different way we can look at this now that we have the tools of conditional probability available to us. Now, you'll notice that our basic formula for conditional probability is that the probability of A conditioned on B is equal to this quotient. But what we can also say just as easily is that the probability of B conditioned on A is equal to still just the probability of B intersected with A divided by the probability of A. Now this is the exact same equation, just swapping the B's and the A's. So it's still the conditional probability. We've just renamed them to make more sense for what we have available to us here, because all of our conditions are a B conditioned on an A, or a B complement conditioned on an A or an A complement. So in this case, we can also look at this equation and kind of rearrange it for a second. So we could say, instead of the probability of A conditioned on B being equal to the intersection of A and B, the probability thereof, divided by the probability of B, we could actually rewrite this and say that the probability of A intersected with B, or of B intersected with A, is equal to the probability of B conditioned on A multiplied by the probability of A. And again, I'm just taking this probability of A and moving it over. I'm multiplying both sides of this equation by the probability of A. Well, with this information in hand, I directly on my model have the probability of A and the probability of B conditioned on A. So we've shown that conditional probabilities really define this equation for us. So rather than just guessing and saying, oh yeah, we're supposed to multiply these two values together to get the right value, we have another way to show that this equation holds true. Now, all that being said, to find the probability of A intersected with B, all we have to do is multiply the probability of A, and actually to keep these terms the same, we'll say the probability of B conditioned on A, which is 0.99. We multiply that by the probability of A, which is 0.05. And we find that that is equal to 0.0495, or just under that 5% chance. Now, we can also look at a different problem. Let's say that we want to find the probability of B occurring, right? Well, in this situation, there are two different legs that we need to care about. And so we can look at this as we really want the sum of two terms. So to find the probability of B, that's going to be equal to the probability of A intersected with B plus the probability of A complement intersected with B. And this may look somewhat familiar. This is a rule that we kind of implied in a couple lectures ago. And so we can very easily find out the probabilities of both of these because these are just leaves on our tree. And we already showed that we can multiply the two branches together to get the end result of each leaf. So in this case, we're looking at this leaf, and then A prime intersected with B is this leaf. So if we multiply this path and add that to the product of this path, we have our answer for the probability of B. So the probability of B is equal to, if we look at A intersected with B, we would say that that is 0.05 multiplied by 0.99 plus on the lower path, 0.95 multiplied by 0.1. And if we add all of these together, we'll find that that is equal to 0.1445, or a probability of just under 15%. So the probability now, what we've established is, without directly knowing what the probability of something registering on a radar is, but with the conditions of an airplane being our first stage, we can now say that the probability that something registers on the radar, irrespective of whether there's an airplane flying above, is roughly 15%. Now, the last thing that we'll look at here is the probability of A given that B has occurred. And we're looking at this a little bit differently now. Instead of saying what we said before, which is what's the probability that something registers on a radar dependent on whether there's an airplane flying above, we're saying what is the probability that there is an airplane flying above if something registers on the radar. And to do this, we'll take some of our previous information that we had calculated and turn that back into an equation that we can use. So the first thing that we need to find is the probability of A intersected with B. Well, we found that earlier, as you may recall, and that probability was equal to 0.0495. It was this 99% multiplied by 0.05. Now, the next phase here, we need to find the probability of B. And the probability of B is something that we found on our previous page. And if we look back, we said that that was equal to 0.1445. So if we plug that in, 445, then all we need to do is divide these out. So the probability of A conditioned on B is just equal to 0.0495 divided by 0.1445. And if we multiply that out, we'll find that it's roughly equal to a third. Specifically, it's 0.343, and that goes on. But what we found is, with just this information, what's given to us in this model, right? A probability that an airplane is flying above, and then a probability that a radar registers based on each state, we can now determine the probability that an airplane is flying above just based on the state of a radar. We can turn this problem on its head, if you will. And what you'll find is that the three things that we've established here, the probability of A intersected with B, the probability of B, and the probability of A conditioned on B, are really three tools that we'll use over and over and over again through this course. And they really form the foundation of being able to do probability well. But before we really dig in too much deeper with these, let's go ahead and generalize them. And that'll happen in our next segment on the multiplication rule.